Hi, I'm Anders Lundström and I will present our paper Making Crank-Powered Interactions that are written together with Ylva Feneus. Our work focuses on the design and prototyping of interactive systems that are limited in energy usage to our bodily capacities. Technology not only powered, but also driven and controlled by human bodies without the need for batteries. This is referred to as human-powered interaction. In this pictorial, we will focus on our experiences with cranking as a mode for controlling and interacting with such self-powered devices. While apparently limited by its restricted and old-fashioned mode of operation, we see reasons why hand cranking can be interesting for interaction designers to explore. Cranking was once the main mode of interaction for early pre-electric industrial and mechanical uses, with well-known examples sketched out by Da Vinci and Pulham. In the pre-electronic age, cranking became prominent for powering the semi-automatic functionality of calculators, music boxes, gramophones, as well as early film cameras and projectors. Cranking is simply everywhere one looks in the history of media technological devices. In our work with 70 interaction design students, the by far most common route explored has been various forms of cranking. In this talk we will summarize our insights from these projects and our own work on human power. We and our students have explored this topic using many different methods such as hands-only scenarios, role-playing, low-fidelity prototyping, Soma trajectories, Wizard of Oz and UX videos. These methods have all proven useful in exploring aspects related to the broader circumstances and in particular the mode of bodily engagement. One basic parameter concerns the scale of movements, ranging from small fingertip manipulation to large full body movement, but also what plane in space the cranking is taking place. Other aspects include cranking direction and the experienced sense of effort of slow and large cranking movements in relation to smaller and faster movements. Another challenge often noted concerns how to prototype the appropriate sense of friction or effort, which is a central part of the user experience in all these scenarios. However, although we have seen many intriguing design ideas by our students, many of these concepts have been far from technically viable. Questions concern how much force would be needed for a certain scenario, what physical size or weight the generators would need to maintain the envisioned system function, how much energy is needed to power a Wi-Fi connection or display something on a screen. Apart from material knowledge regarding the energy requirements, there is also a need for understanding the mechanical functionality. For instance, the function and possibilities of adding gears and solutions for fabricating and mounting mechanical parts. Without any technically working demonstrators to play with hands-on, it becomes difficult to imagine the space of possibilities and thereby generate meaningful or viable ideas. In our own work, we like to highlight learnings from 3 different demonstrators. First, the hand crank quote reader allows scrolling back and forth through famous science quotes. The quotes stay on screen after cranking since we used an e-paper display and preserves its state between cranks. One thing learned from this exploration was the importance of working with display materials. It is difficult to read on a display while cranking, and regular displays turns off when cranking stops. Using an e-ink, it is possible to read in between cranks, and interestingly, this also created the illusion that the device was always on, also when the system had no power. Secondly, the email machine was built to explore hand-cranked communication via Wi-Fi. A person cranks until the progress bar indicates that the email is sent. An important part of this demonstrator concerned learning more about the human efforts needed to send various emails. For instance, a 32 kilobyte message took about 1 minute and 10 seconds of cranking to transmit. One important insight was the importance of feedback, both to communicate if sufficient power is generated and to illustrate the progress made with the transmission. The latter was particularly important because of the slow qualities of this design, since it was tedious to crank. Thirdly, we prototyped a wireless PowerPoint clicker device. so that the presenter could wirelessly step back and forth in a slideshow presentation on a computer using the crank. Our main learnings concerned that in contrast to the other examples, this was actually a viable and attractive application that felt natural and intuitive to use. This highlighted that there are interesting applications for human power if we only start exploring this design space along with real-world use cases. One of the main lessons from the student works was how technically difficult it was for our interaction design students to practically realize their ideas and work with human power as a design material. Our conclusion was that we need to provide tools to allow for exploration of this design space and create learning experiences related to the main material properties of human power. We need to make a design material. As a result, we designed and built a series of tools to support our students. First, we made a human-powered little bit to enable early experiments and easy crafting of human-powered designs by leveraging on the little bit's ecosystem. The bit has 3 output snaps and 2 outlets provide the speed and direction of cranking. Through hands-on experience, our students noticed that certain actuators are more demanding than others, indicating that the little bit provided a very concrete learning experience on the power requirements of different actuators. Secondly, because the little bit is limited and students tend to use Arduino Unos, we created an Uno shield to enable a versatile entry point to human power and facilitate exploration. The shield provides appropriate power management, detection of direction of turn, and speed of cranking. Here is one example student project where the shield was used. The generative art machine explored the material conditions of software and algorithms in the context of human-powered interaction and e-ink displays. The most obvious insights from our experiences of working with interaction design students concern the current lack of available resources, both in terms of guidelines and instructions and in terms of readily available technology to use when prototyping and testing out these types of interactions. This led us to develop tools, demonstrators, and resources needed to get the students going. Although our tools overcame initial technical hardware hurdles, many issues remained concerning how to best program microcontrollers and how to use sensors and actuators for interesting user experiences. One of the main differences is that the design space changes from an always-on regime to power in chaotic bursts. This needs to be managed in the software and also requires material consideration and exploration. Interestingly, these issues have not yet been reported on in the literature, suggesting that we need to shift focus from hypothetical and theoretical assumptions around human power to practice. It is important to stress that because of the radical difference of battery-free human power devices, we need to make functional prototypes in order to understand the real limitations and qualities of this technology. This is not design as usual. We conclude that much work remains to better support interaction designers interested in human power. More research is obviously needed to both look into the details of how to design devices and more conceptual aspects of this design space. How can we work to make pleasurable, meaningful, and aesthetically engaging interaction using power generated by our bodies? We see much potential in developing more structured resources to better support future students, makers, inventors, and designers to develop new interesting human-powered applications. Thanks.